Hello class, in this video we will learn about hemoglobin and the chemistry behind its role in the human body, and finally we will learn about carbon monoxide poisoning and its corresponding treatment plan. Let's first discuss about hemoglobin. Hemoglobin is a large protein found in red blood cells. Each red blood cells contain millions of hemoglobin molecules and they play an important role. Hemoglobin is responsible for binding or attaching oxygen from the lungs, which is then transported and released to the other cells around the body. The reversible reaction between hemoglobin and oxygen can be represented by the following worded or chemical equation down below. Chemically, hemoglobin is represented by the symbol Hb4 because the protein is made up of 4 subunits where each subunit can bind onto one oxygen molecule, which is a total of 4 oxygen molecules as illustrated in the animations below. I would like to add that this is the American spelling of the word hemoglobin. Hemoglobin should be spelled as H-E-M-O rather than H-E-M-O for the word hemo. The dynamic process in which hemoglobin attaches and releases oxygen can be explained using Le Chatelier's principle. In the lungs, there's a high concentration of oxygen, so equilibrium will shift to the right, favoring the formation of oxyhemoglobin. However, as the red blood cells are transported away from the lungs, the concentration of oxygen decreases. The reverse reaction is then favored, which releases oxygens. Consequently, the cells are able to uptake or absorb the oxygen, which is then used for cellular respiration and for the cell to perform its biological functions. Now that we have developed an understanding of hemoglobin and how it works, let's now talk about carbon monoxide poisoning. Carbon monoxide poisoning occurs when carbon monoxide is inhaled and builds up in the bloodstream. Because it's a colorless, odorless, and tasteless gas, carbon monoxide is often described as a silent killer. Carbon monoxide is formed as a product from the incomplete combustion of fuels and hydrocarbons, where it's typically found in cigarettes and exhaust gases and areas of high traffic pollution. Due to a lack of oxygen getting into the cells, symptoms of carbon monoxide poisoning includes dizziness, chest pains, confusion, blurred vision, headaches, shortness of breath, and nausea. In the worst case scenario, prolonged exposure to carbon monoxide can lead to death. Let's unpack and learn the chemistry behind carbon monoxide poisoning. It turns out that carbon monoxide can also bind to hemoglobin, and the reaction between hemoglobin and carbon monoxide forms a protein complex called carboxyhaemoglobin. This is represented by the following worded and chemical equation. Unlike oxyhemoglobin, forming carboxyhaemoglobin is not desired because now the red blood cells are no longer delivering oxygen to the muscles and organs around the body, thereby preventing cellular respiration and the organs from performing their normal functions. To demonstrate what I mean by this, look at the following animation. In an environment where there is no carbon monoxide, hemoglobin binds to oxygen and the red blood cells transports this to the heart. This allows the heart to function normally. When carbon monoxide is inhaled, it is now attached to hemoglobin and is no longer supplying the cardiac muscles of the heart oxygen so that it can no longer perform its biological functions. Consequently, we can see that the heart is now beating more slowly and more weakly. This is one example of carbon monoxide poisoning, but as I mentioned earlier, other symptoms may also arise. When both oxygen and carbon monoxide are present, both of the reactions below are described as competing equilibria. This means that both oxygen and carbon monoxide compete to bind to hemoglobin. However, the extent of the reaction and the equilibrium constant for the formation of carboxyhemoglobin is 2,000 times larger than the formation of oxyhemoglobin. This has two implications. Firstly, a large equilibrium constant for the formation of carboxyhemoglobin suggests that carbon monoxide has a higher affinity for hemoglobin than oxygen. Because of the higher affinity, carbon monoxide can effectively displace the oxygen that's already binded to hemoglobin. Secondly, a large equilibrium constant value suggests that the forward reaction is more likely to take place, hence the formation of carboxyhemoglobin is significantly favored. Additionally, because hemoglobin is now used up by this forwards reaction over here, Le Chatelier's principle states that the reverse reaction for the formation of oxyhemoglobin is favored as compensation. As a result, we can see that carbon monoxide poisoning will effectively impair the transportation of oxygen around the body. Fortunately, the effects of carbon monoxide poisoning can be reversed if a patient or victim is treated as early as possible. Because the reaction is reversible, carbon monoxide poisoning can be counteracted by administering pure oxygen or moving the person to an open environment with plentiful oxygen. According to Le Chatelier's principle, having more oxygen will shift the equilibrium to the right in favor of the formation of oxyhemoglobin to partially oppose the addition of oxygen. Furthermore, it will shift the equilibrium to the left in favor of the dissociation of carboxyhemoglobin, or the reverse reaction in other words. This will then free the hemoglobin protein so that it can now bind to oxygen. Overall, more oxygen shifts the position of the equilibria such that it unbinds carbon monoxide from hemoglobin and favors the formation of oxyhemoglobin, which increases oxygen carrying capacity and allowing oxygen to be delivered to the oxygen-deprived cells. There are two VCAA short answer questions that are related to carbon monoxide poisoning. In this question, it wants you to use Le Chatelier's principle to discuss the changes in Tien's breathing in the park and in the high traffic area. In your answer, we need to refer to competing equilibria, and we may also use equations. Pause the video now if you'd like to attempt this question before hearing my response. To answer this 5-mark question, I started off by explaining what happens when Tien is running in the park and included the chemical equation for the formation of oxyhemoglobin. This will probably give me 2 marks. For the next 2 marks, I've then discussed about how this changes when Tien now runs in an area with high levels of traffic and provided the chemical equation between carbon monoxide and hemoglobin. For the last mark, I then talked about how oxygen and carbon monoxide compete with each other for hemoglobin, but because hemoglobin has a high affinity for carbon monoxide and the equilibrium constant for this reaction is greater, this favors the formation of carboxyhemoglobin, which accounts for Tien's shortness of breath. A similar question was also asked in the VCAA 2017 paper. In this question, we need to compare the equilibrium constants between the two equations and provide what conclusions we can derive from this particular question. To answer this question, I responded by saying that the equilibrium constant value for the second equation is a lot greater than the value for the first equation. Although both carbon monoxide and oxygen are competing for hemoglobin, hemoglobin has a higher affinity for carbon monoxide and binds more favorably, hence the equilibrium constant for K2 is larger than K1. This is the end of the video. Hopefully you found this video helpful. Thank you for watching, and I'll see you guys again in the next one. Bye.